Well, good morning, y'all. It's an absolute honor and a privilege to be here. There's a lot of gentlemen and ladies in the room that have helped me throughout my life. There's folks in the room here that helped me pay for my master's and bought my show pigs as a kid to help send me to college. And then there's folks that actually trained me when I was in college. Dr. Banzik was my master's advisor. It's an honor to stand in front of y'all and give you a little bit of an introduction of why West Texas is so phenomenal. There are a lot of geologists that we lost in the past 3 years that were structure guys and that helped me build this map. And so one of them was Dr. Bill Thomas. He was got the third Ph.D. ever given from Virginia Tech, one of my mentors at University of Kentucky. The other one was Blaine Hall, wonderful geologist from down in Big Bend. He directed a lot of great science, and there is a field trip that is going on here in the next couple of weeks, put on by the GSA in his honor, put on by Dr. Pat Dickerson and Dr. Joe Satterfield. If you're interested, it's a 5-day trip going through the tectonics of North America and the fabrics of North America, which West Texas holds the key to understanding global tectonics, actually. So what I want to do with you is share with you a little bit this morning about what makes West Texas phenomenal geologically. And I'll take you on a little history tour, about 1.8 billion years. And then we'll get into what makes water unique and interesting out here, which is why we're in the room. But what we forget is, where does it actually start? Where does it come from? What's the ages of this stuff? And how does it have a fingerprint? So I'd like to give you an introduction to what we're working on. This map here that we're working on, this is what they call the Appalachian Mountains. The bottom of the Appalachians, it's the seventh orogeny or suborogeny associated with the Appalachians. They are exposed in Marathon, Texas. So you can lay your hands on the Appalachian Mountains. They're also exposed in my backyard. You can see them from Balmorhea, Texas, if you really squint. They show up in Oklahoma a little bit. This is an interesting mountain building event or orogeny. It's about 250 billion years old. It is responsible for the creation of the Permian Basin, which is dear to all of us. It's a kind of interesting how this occurs because it's an overprint of a pre-existing orogenic event known as the Grenville. And so the Grenville is exposed out here by Van Horn, Texas. And it's the oldest tectonic event associated with North America. It's about 1.8 billion years old. It's responsible for the emplacement of the Llano uplift, which I'll get to in a minute, in central Texas. So this Llano uplift part, I actually love this map. This Llano uplift part has been uplifted due to the second orogeny. What happens is you have Earth, every continent on Earth came together into a supercontinent, and it breaks apart. So about 1.8 billion years ago, they come together into a supercontinent called Rodinia, and then they break apart in the Laurentian, Baltic, and all these great places that we hear about. And then they come back together, and they form Pangaea due to this line. This is the bottom part, the most recent part of the formation of Pangaea occurs due to the Marathon-Ouachita thrust belt. And then they break apart again into the modern continents. West Texas has been hit or deformed multiple times. So it gets deformed. We see faults running in the northeast-southwest direction. We see some running northwest-southeast. We see some running north-south. We see some running east-west. It is an impossible puzzle to solve. We've been mapping tectonic areas of West Texas now for over 30 years. I have personally. And we are just now beginning to almost understand what's happening. And everything we do, we have to go publish a new paper on. Dr. White always publishes a new paper and says, well, White 2015 was wrong, now White 2018 is right, and then so on. So, you know, in academia, we reinvent ourselves with our ideas a lot. So as we move forward, when we see this formation of the mountain event, we see a whole lot of stuff occur, but the Midland Basin begins to form. So the Appalachians get shoved up over here in central Texas. Picture something almost as big as the Himalayas, most likely, huge mountain range. The Permian Basin is referred to as a flexural basin. It is a weakness in the Earth's crust, and it begins to get loaded from river systems coming from a high mountain range over here by Llano in our direction. As it begins to load, it begins to fail. The lithosphere thins, and you begin to see this basin form. The basin continues to load with sediment, and it begins to actually sink. So when we're looking at the basins and how they're actually located, it's broken into three subbasins. The Permian has the Midland Basin, the Delaware Basin, and a later basin known as the Midland, which is off over here, or the Marfa, which is over here in this region. They're connected by channels. So the deepest one's the Delaware, and as they begin to sink, there's faults that form. Now, we lost one of the best geologists that West Texas has ever seen this year, and a dear friend of mine named Steve Shaw, and he used to predict where these faults originated. And these faults, he would say, would come from the basement and propagate upward. And as we begin to load this system, the faults were syndepositional, meaning the faults are getting covered up as they're dropping. And so we see these just great tectonic frameworks occurring out here. And how this all happens is just fascinating. So in the history of it, the basin begins to form, then it begins to drain. Midland Basin drains first. Delaware winds up cut off and becomes a starved system, produces lots of evaporite rocks. And then we begin to see it drain out toward the Mexico side. We fast forward a few million years, and we wind up underwater again. And so just as an overview before I get into this, the mountain range that's over here is known as the Rocky Mountains. And so this is the Laramide fold frost belt. They cross right here in West Texas. And so this one here is aged at about 66 million to about 28 million years. This is a compression event coming from compression from the west. So we see a major tectonic event. It is responsible for the West Texas volcanic province. It is why we see the volcanoes and things out here. So we have a tectonic event here, 250 million years ago, formation of a basin, major uplift. Flooding occurs, and then we start seeing a second tectonic event at about 66 million years ago. Then from 20 million years to the present, we see modern basin range extension. And North America, if you picture everything from where we're standing in Pecos, Texas to Bishop, California, compressed by 100%, that's what it looked like when these mountains were formed. And then they begin to extend. And we see, if you drive west, you'll see a mountain range, flat area, mountain range, flat area. That's basin range. It goes all the way to Bishop, California, home of mule days, in case anybody wants to go with me. We go out there quite a bit. Interesting place. Basin range starts off with a full-on extensional system, followed by a shear system. It's an interesting thing. Now, in the middle of these formations of the basins are here, the ones we're interested in, Delaware and Midland. This is a great image that I liberated from UTPB, and it shows where your Midland and your Delaware is. This is a flooding event. All of your rocks of Permian age are in this basin. That's a cross-section of the basins from east to west with all of the rocks. This is the Central Basin Platform, Midland Basin, Central Basin Platform, and then you have your Delaware, a lot deeper system. The wells that were discovered out here that we all tend to overlook were originally drilled in Westbrook, Texas. Anybody know where Westbrook is? Thriving metropolis off I-10, I-20 up here outside of Big Spring. But the ones that we tend to remember are this dude, Santa Rita #1, down outside of San Angelo, Texas. And so it was our version of Spindletop. And it also created a frenzy out here. And so people began to just flood to the San Angelo area and start drilling in the late 30s into the 40s. And that's where we start seeing the oil boom start. And then we follow the boom all the way out into this area as we progress. The provinces of Texas geologically are fascinating. So the part up here that we see is this orange part, that is the high plains. The blue part are all the Permian rocks exposed in Triassic. And then the green part is the Cretaceous. The black part there is the Llano Uplift, its own province because it's so fascinating that it is made of a granite pluton. I'll show you pictures of it in a minute. And then we have the coastal plain system, which is all designed of gravels and splays coming off of mountain ranges associated with the Rockies. And then we have the Trans-Pecos volcanic province out here. First thing you got to remember is Earth, specifically where we're standing. If we drilled a hole to the granite basement under our feet in Pecos, Texas, we will find fascinating things. Earth has been underwater, or at least this continent has been underwater 6 different times. When we have continental flooding, they refer to this as salt sequences. And so a salt sequence is when we actually get put underneath an ocean and we begin to deposit sedimentary rocks. This is where we see our carbonate rocks, our original rocks associated with our oil coming from, and the actual rocks that make up our aquifers. The first ones we see, there's the salt sequence, Tippecanoe, and then we get into the Permian sequences, and then we get into what they call the Zuni and the Tejas. So this here's the geologic time scale. This is your Paleozoic, Mesozoic, and Cenozoic. The rocks that hold most of our aquifers are up in here, except for a few. So the stratigraphy that you start seeing in aquifers is fascinating. And we have some deep aquifers under us, but most of them are considerably shallower. So we're looking at things within 2,000 foot of the surface. So, and they are easy to contaminate. The Llano uplift is cool in its own regard. This is what the basement actually looks like. When we drill and we hit the term basement, we're talking about a Precambrian age rock older than 540 million years old, and it is the crystalline basement that underlies the entire continent. It is fascinating. It's exposed here, and it's exposed here in Van Horn, Texas, right off the highway at I-10. What we see here is a granite pluton, large in placement. It's considered a laccolith or a batholith. What's really fascinating about it is this is where you can see the very first continental flooding event in the world. And it is known as the Great Unconformity, where you have the granite basement and then a little rock called the Hickory Sandstone, which is one of the most famous rocks in Texas because it is the first flooding event that covered the salt sequence, but it's the first frac sand. It's perfectly spherical sand, and that is where where the frac sand began to come from back when we were fracking the Austin chalk and things. That's where we found the sand that was spherical enough to send down a well until recent times. What it's used for now is they use it on all the AstroTurf that you see in the NFL games. You ever notice the dust pop up when you're watching one? That is dyed sand from the Hickory Sand here in Central Texas. Pretty interesting place. It's a fascinating rock. You can see great outcrops of it outside of places like Hoover Point, where it is exposed. And if you get a chance, this is down right outside of Llano. So the next major flooding event that we see the rocks out here of, so we'll have all this stratigraphy put in here. And a thing that geologists are happy about, which I have probably really massacred, is we love terminology, right? And I was on a phone call the other day that some folks in the room had put together, and even we confused ourselves. So when we start looking at terminology, let me simplify it a little bit. Rocks are fun to lick. That's why we got into it. All right? That's all you got to remember. Rocks are fun to go check out. The geology in this region, we get so excited that you can't get us back in the truck. And geologists are goofy. So we got to remember that. But here's the point. All the stuff you're going to learn today, that all the speakers after me are going to talk about, you're going to have these technical terms, right? So let me simplify it. The only difference between a groundwater guy and a plumber is plumbers are smarter, hot water's on the left, and shit runs downhill. So you got to remember that. And if you can remember that, then this stuff becomes a lot more simplistic. Water starts off from rain, and it's going to have a pH that's slightly acidic, and it's not going to have anything in it. And it begins to come in contact with the rocks. And over time, it'll eat up a chemistry, and it'll develop a signature, like our fingerprint, that allows you to pinpoint where it's coming from. So each individual aquifer that we're going to talk about is going to have its own specific fingerprint. And it gets its fingerprint from the rock. And if you don't have the geology figured out. You can't figure out the groundwater period because you can't figure out where the water's moving. You can't figure out where it's going. And I'm going to pick on the younger geologists and engineers in the room. If you don't understand how to make a geologic map, you're not a geologist yet. So y'all got to come see us so we can train you up, because the computer doesn't do it for you. If you put junk in a system, all models are going to be wrong. Some are useful, but you're still wrong. So as we prolong through this endeavor of misery, I put together 45 pages of excruciating chemistry for you. And at any point in time, I use a term that you don't savvy. Please raise your hand and let's fix this, because we're here to learn. And geologists, our geomorphic dictionary is almost as big as the regular dictionary. So that's why we wind up over in this weird world. So here we go. You ready for some more terms? All right. This here's the Cretaceous Interior Seaway North American's flooding event, Zuni transgression, where North America winds up flooded for the last time, pretty much. This is the age of the dinosaurs, which is recorded out here in West Texas beautifully. All of our Cretaceous rocks from the antler sand up to the surface, pretty much. All of the Cretaceous sequence exposed in West Texas. And we see it in Balmorhea, we see it all over. We have the seaway that floods everything between these two mountain ranges. And now we got some just beautiful rocks. And it produces some reef deposits, which become aquifers. This is fascinating to me. There's your basins up here. This is all an ancestral deep ocean basin. And you can actually see a lot of this exposed in West Texas. And so this is the last flooding event of the Zuni. So these rocks get stacked up due to flooding events. There's floods, we lay stratigraphy down, they get exposed, they erode down. And then we have gaps of time that get missing, because as you erode rocks and it gets transported somewhere else, there's a gap in time, right? So we have these transgressive regressive sequences, and they produce layers. Now later on, these layers become the reservoirs for our oil or for our rocks, and we have source rocks and pay rocks and all the stuff that we start talking about. It's important to remember we will have things like recharge zones, typically on your highlands. This is a cross-section of what an aquifer would look like, where water can move from high to low. Remember, it goes downhill. It follows pressure. And so when we drill a well or you have a spring, the only reason you have a spring is because you have pressure at that system and it's been cross-cut by a fault or something and the water's flowing. Other than that, we don't have a spring. So if you drill in above the spring and you pump a lot, you will dry up a system. That's what occurs. And so we've seen that last year or 2 years ago. Mr. White gave an extremely wonderful talk where the aquifers out here had been depleted so much that like 30-some springs were dried up from the time when he was a kid till now. It was one of the best talks I'd ever seen. He had pictures of them when he was little versus pictures of them now. So we're overexploiting our resource to a degree. Here's what the compositions of these aquifers wind up looking like. So as we move forward, you got major ions. This is what the signatures are. They're calcium, magnesium, potassium. These wind up in a solute. Water is known as the universal solvent. It will dissolve anything it comes in contact with and meet equilibrium with it given enough time. So these are when we start seeing diagrams of aquifer chemistries and what they are. These are our major players. This begins to form our fingerprint, our metals and things of that nature that we see. Other parameters we start looking at are just physiochemical parameters like pH and specific conductance. The driving factors of water quality are always fascinating. These are your basics: evaporation and weathering and ion exchange and nutrient cycling. And then we get into contamination. So I wrote a whole dissertation on tracking fecal material through aquifers. It was other scat, you know. If you read it, you get it. It was a thesis that was interesting. But we can track things like pharmaceuticals. 280 emerging pharmaceuticals in water supplies in the eastern part of the nation where they wind up in our drinking water. We can't treat it. It just, what's the solution to pollution? Dilution. So every little town pulls it out, sends it through its water treatment system. We drink it, we urinate it out, it goes through the system. Hell, we're all on Prozac. By the time you get down By the time you get down to the river, yeah, this is no joke. One of my professors at University of Kentucky predicted we'd be drinking water in New Orleans when we're at Mardi Gras that's been through approximately 11 human kidneys. And I don't know how she calculated that. We can call and ask her. But weathering and chemical weathering and physical weathering is how we get these formations. It's how we form caverns. We take a rock that's like a carbonate rock, which is our dominant ions out here in West Texas, and we begin to put it in contact with rainwater. We begin to etch it. We begin to see these chemistries start. In Kentucky and Florida, we see caverns beautifully. This is where I went to school for karst. And in West Texas, we see the same thing. What happens when you weather out carbonate rocks? What's the byproduct? It becomes clays. And all we see in West Texas are clays. There's all kinds of clays out here. And so as you begin to go through this process, rocks get reincarnated. They start off as crystalline rocks, they get weathered down, reincarnated, moved around, turned into sedimentary rocks, eaten up some more, then they gradually get reincarnated or recycled through these big events. It's a whole cycle. And our job as scientists is to try to explain how this works and to try to understand an acid-base reaction and how it functions. And then to try to get somewhere to where we can explain it. And then we have to take the science and utilize it to try to make the best educated decision we can for the general public's well-being. So I am not a very good scientist. I have lots of degrees. I have a professional licensure that guarantees that I am minimally competent to practice geology in the state of Texas and about 20 other states. But does that make me know much? No. All we do is we do our best and we keep working at it, right? And so as we begin to move forward, these are the complexes. And it goes on and on and on. And I hope y'all can get a copy of this. This is our stratigraphy that we're interested that you'll learn about today. All the springs that you'll hear about from the southern part of the county are pretty much in this age of the Cretaceous. There's a few of them that are down here in the older ages when we get into the Dockum and some of the other aquifers that we'll learn about. So we're looking at Mesozoic and Paleozoic rocks is the ages we're going to be looking at as we move forward and we see our talks today. We take these chemistries from a general chemistry breakdown and we can fingerprint them and they begin to tell us what a water does. They can tell you flow past time in the subsurface. And then we get into weird theoretical physics, you know. So there's this great joke about a geologist. You got an engineer, a geophysicist, and a hydro guy, and they're standing on the same problem. So they asked the engineer, "What's 2 + 2?" And he goes, "Oh hell, that's easy. That's 4." Done. All right, engineer, he's gone. Then they asked the geophysicist, "All right, what's 2 + 2?" And he kind of looks funny. He goes, "I'm gonna skip." And he goes to the groundwater guy and he asks him, "What's 2 + 2?" And he goes, "That's easy. It's 4 ± 2." Then they get back to the geophysicist. He's watched this stuff go on and he goes, 2 + 2. He goes, "What do you want it to be?" So every one of us has a different point of view that we're coming from, and everybody thinks they're right, and everybody can make it what you want it to be. It's important that we study this data and we use it for the proper purposes. And when we get into the aquifers of this area, I've done a lot of research in this region. Here's Reeves County. These are your Edwards Trinity aquifers, exposed, and then the other ones that we start seeing in our minor aquifers. These are like your Dockum and Rustler and Antlers that we'll see. This is Jeff Davis County, Reeves County, beginning of Pecos County. I want to point out something here that's fascinating that most of us don't recognize. Aquifers continue across boundaries of county lines, but our water district stays in Reeves County. It's separate from Ty and his group, and it's separate from Uncle Johnny and his group, and it's separate from the Culberson County guys. So now we got a problem. So when you draw a line and you got an aquifer that's crossing a line, now we got a geopolitical issue. there's lots of data that I've put together with the tops of geophysical logs from back in the 50s and actually made maps and structural maps of the subsurface of our region around Balmorhea, Central Reeves County. But I'm out of time according to this. Let me go over here. I'm gonna end on this beautiful map. I'll go one more. I screwed it up, sir. We can end on this map. I appreciate y'all listening to me, and I apologize. I should have gave you a warning that you could come out dumber from listening to me. That's what, no, I mean, I rambled on. I covered a lot of country, a lot of geology, a lot of time, a lot of stuff went on. But it's important that we remember where we're standing is here, and it's in the middle of all of this going on around us. It's an ultra complex area. There's nothing simple about it. And we learn something marvelous every day about it. And it is the key to understanding global tectonics. And I cannot stress that enough. And we've been lucky enough to publish our papers lately with Dr. Dickerson and Dr. Satterfield. And might want to look at some of them. And the other thing is fascinating is geology doesn't stop at national boundaries. So we're in Mexico a lot mapping this stuff now. But I'll be happy to answer any question we may have. All right, I'm getting better at this. No questions. All right. All right, thank you.